السلام عليكم ورحمة الله وبركاته. طلاب المرحلة الأولى إن شاء الله زينين. Linear Algebra 2 First Level Lecture 13 Chapter 4 Euclidean Geometry of Rn. This is Chapter 4. Start from today. Chapter 4 Euclidean Geometry of Rn. The first we take definition of dot product. Definition of dot product. Let xy belongs to Rn times 1. We define the dot product denoted by this is dot product between two vectors x and y belongs to R. This belongs to Rn times 1 by x dot y is equal to x transpose y, and this is equal to x1 times y1 plus x2 times y2 until plus xn yn. The dot product is a mapping. This is a mapping that means function from x n times 1 cross n Rn times 1 to R, i.e. this is function x dot y, this is dot product Rn times 1 times cross Rn times 1 into R. And now we take this is example. Let V equal 1 2 3 4 5 and W equals 6 7 8 9 10, and this is by definition V dot W is equal to V transpose W. Look like this in definition of dot product. So this is will be V transpose will be the column will be row 1 2 3 4 5, and this is the column, and this is definition of product of matrix. This by this and sum 6 plus 14 plus 6 plus 14, and this is 42, and this is 36, and this is 50, and this is equal to 130. The dot product can be defined the length or norm. We can use the dot product to define length and norm of vector and the angle between two vectors. This is page number 1, and here we will define the length and norm. The length or norm of Rx belongs to Rn times 1 is a real number, which is defined by this is norm. This is symbol of norm of x. Norm of x is equal root of x dot product x. Furthermore, let xy be non-zero vectors in Rn times 1. We define the angle between the angle theta between x and y by cosine inverse x dot product y over norm x norm y. This is cosine inverse of this angle is the theta between two vectors x and y. R together with these definitions of length and angle form a Euclidean geometry. النظام الإقليدي هندسي الإقليدي. Euclidean geometry. This is إقليدي. This is geometry هندسي. Proposition. Suppose z belongs to Rn times 1 and C belongs to R, then x dot y is equal y dot x, and x dot y plus z is equal to x dot y plus x dot z. Move here and here. C x dot y is equal to cx dot y equal to x dot cy. and x dot x is greater than or equal to 0, and x dot x is equal to 0 if and only if x equal to 0. This is page number 2, and now we prove this proposition. Prove 1. X dot y 1 x dot y is equal y dot x. This is easy. X dot y is equal summation I 1 to n x I y I. This is by definition of dot product, and we can change mute x I y I, mute commute. This is in R commute. We can change them. This will be exactly the dot product between y dot x. So we get x dot y is equal to y dot x. Now prove 2. X dot y plus z is equal to sigma I from 1 to n x I y z plus z I. This is equal to some sigma I equal 1 to n, move here and here, and I also I move here and here. This is equal to x I y I and x I z I, and this is move here sigma here and here will be sigma I from 1 to n x I y I plus sigma I from 1 to n x I z I, and this is exactly the dot product between x and I, and this is exactly the dot product between x and z. And prove 3. If c x dot y is equal to c sigma I from 1 to n x I y I, and this is equal to sigma I from 1 to n c x I y I, and exactly this is equal to c x I and y I, and this is also is equal to x I sigma I from 1 to n x I c y I, and this is exactly the is equal to cx dot y, and also this is equal to x dot cy, dot product cy, and this finish proof or 3. Now proof 4. Now we will prove 4. Proof 4. X dot x is equal to sigma I is equal to 1 to n x I, and this is equal to sigma I equal 1 to n x I square. This is xi square because the same, and this is for all I. Now this is, that means this is greater than or equal to 0. This is greater than or equal to 0 because this is square. So this is the first part, and the second part of the 4, if x dot x is equal to 0, that means this implies sigma I from 1 to n xi dot xi equal to 0. Also this is implies, which implies that sigma I from 1 to n xi square is equal to 0. This is implies that, because this is positive numbers and this is sum, so this is all of them xi square equal to 0 for all I, and this mean xi is equal to 0 for all I. So that means this is implies x is equal to 0, and the opposite side, if x equal to 0, that means implies, which implies xi equals 0 for all I, and this is, if xi equals 0 for all I, this is implies that xi also equal to 0, and this is implies summation all of them will be also 0, and this implies summation xi dot xi equals 0 times xi equals 0, and this is by definition of inner product xi x xx. This is inner product of x. So this is we get this is 4 finish 4 for both sides. This is page number 3. And now we prove the Cauchy Shwarz inequality proposition. This is call it Cauchy Shwarz inequality. Now prove this if xy belongs to Rn times 1, then absolute value x dot y, this is absolute value, less than or equal norm x times norm y, for all xy belongs to Rn times 1. Prove. Let xy belongs to Rn times 1. Now if either x equal to 0 or y is equal to 0, then the inequality is clear true, because if x is 0, that means x times any vector will be 0, and this is x will be 0 also, and this so equality here x 0 equal to 0, or y 0 all the same will be also 0, and this 0 will be this also 0, so we get the equality. Suppose then that both x and y are non-zero vectors, both of them, x and y, both of them not zero vectors. It follows that mean norm x, norm y, both of them not equal to 0. This and this, both of them not equal to 0. And we can define vectors of unit length as follows: x hat is equal to x over norm x, y hat is equal to y over y norm y. Notice that x hat dot x hat is equal to x over norm x times x our norm x, and this is will be equal to 1 our norm x squared. Move here this out, and this is here will be x dot x, because this is still x here, and here x dot x, and this is by definition of norm. We take it the first definition, the second definition of norm is equal to root of x dot x. Norm x is equal to root norm x is equal to root of x dot x, and this we can put here. This is will be this is will be equal to 1 over. This is will be x dot x here, and here this is, if we take here take squared for both sides, will be x squared, norm x squared here will be equal to x dot x, will be equal x dot x. So this is x dot x, put here x dot x instead of this, and now this is we can abbreviate, so this is get equal to 1. So x dot x, x hat dot x hat equal to 1. Also the same y dot y hat dot dot y hat also equal to 1, the same this. So now we have x hat dot x hat equal 1, and y hat dot y hat also equal to 1. Now consider norm of x hat plus minus y hat, and this is of course is greater than or equal to 0, because this is norm and this is square. Here put here square, and this is of course is greater than or equal to 0, and this is by definition of norm here. Also here we come back here, if this squared, so this is x dot x. That means this is the same vector x hat plus minus y hat dot x hat plus minus y hat, because this is square, and we can move x hat here, x hat dot x hat, and this is plus minus 2x hat dot y hat, and this is equal plus x y hat dot y hat, and this is of course we get this is 1 and this is 1, so this is 1 and 1 equal to 2 plus minus 2 x hat dot y hat. Which implies if I move this 2 here, we get minus 2, this is move here, minus 2 less than or equal plus minus 2 x hat times dot product y hat, and you can divide by minus 2, so we get minus 2, this is will be plus minus x hat dot y hat less than or equal to 1 here, because this is minus 2, so this is, we can move here, and this is here because divided by minus 2, and this is mean, and this is mean. This implies this is absolute value x hat dot y hat less than or equal to 1. And this is page number 4, and therefore now therefore noting that x is equal to norm x hat and y is equal to norm y hat. So x dot y absolute value, from where get this x equal norm x, we get it from here. x is equal to norm x hat, and y is equal to norm y hat. From here, from this definition of x hat y hat, we get this both. Now we take x, no, absolute value x dot y, and this is will be equal to absolute value, and x is equal to norm x hat dot y is equal to norm y hat, and this is absolute value. So this is constant and this is constant. You can move out of this is absolute value. This is positive numbers x norm y. Here still x hat dot y hat absolute value, and this is less than 1. This is less than 1. Prove here this is less than 1. So if this less than 1, so this is less than or equal to norm x norm y, because this is less than 1. And now we finished the proof, because we get norm x y dot y, sorry, this is not norm, this is absolute value, less than or equal to norm x norm y. This is finish the proof. I think this is clear. Now take example to compute the theta between two angles. How can compute theta between two angles? Example, two vectors. Let v is equal to 1, 2, 3, 4, 5. This is v. W is equal to 6, 7, 8, 9, 10. This is W. Find the angle. Find the angle between these vectors. Between these vectors now solution. Solve this example. we find norm, sorry, first we find v dot w is equal to 6 and 14 plus 24 plus 36 plus 50. This is times and sum, and this is equal to 130. And also we can compute norm of v. This is equal to 1 square plus 2 square plus 3 square plus 4 square plus 5 square. This is will be equal to 1 plus 4 plus 9 plus 16 plus 25, and this is will be equal to 55. And norm of w is equal to also the same, but here w 6 square 7 square plus 8 square plus 9 square plus 10 square, and this is will be equal to 36, 49, 64, and this is 81, this is 100. This is will be root of 330. And now we can compute the theta. Theta, by definition, theta equal to cosine inverse of x dot y over norm x times norm y, and put here is equal cosine inverse, put here x dot y, here x vw equal 130, and this is equal to root of 55, and this is equal to 330, root of 330. This is will be approximate 15, 21 degree. This theta. Now this is page number 5. Now you take proposition. Let xy belongs to Rn times 1, and suppose C belongs to R. Then, number 1, norm Cx is equal to absolute value C norm x. Number 2, norm of x plus y less than or equal to norm x plus norm y. Now prove 1. This is 1. Let x belongs to Rn times 1 and C belongs to real number A. Now we calculate this norm of Cx square is equal to Cx dot Cx, this by definition of norm, because this is square, and this is equal to C square x dot x, and this is also is equal to c squared norm x square. Since norm of cx greater than or equal to 0. This is norm by definition of norm. Also, always this is greater than of or equal to 0. And if we take the square root from this equality, we get norm of cx root square go out, and this is c square root here, and this is also x. And c square root, this is equal to absolute value of c. This is equal to absolute value of c. Thus, we put here this here, and we get norm cx is equal to absolute value c norm x. And this is finish proof of 1. And now proof 2. Let x, y belongs to Rn times 1. And now we take this x plus y square, and this is equal to, by definition of norm, x plus y times dot product x plus y. This is definition of norm. And this we can here, because this is square, so this is, we have to take absolute value because this is square, and move this here, x dot x plus y dot x plus y. The properties of dot product, and this is equal to x dot x plus x dot y, and this is plus y dot x plus y dot y. Also, this is definition of dot product, and this is by definition of, this is norm of x square plus, this is the same because xy dot y is equal to y dot x plus 2x dot y plus norm of y squared. This is y dot product y is equal to norm of y squared, and this is because there is triangle inequality, this is less than or equal to norm x squared plus 2 norm of x dot y. This is norm of y. This is by triangle inequality, and this is by Cauchy Shwarz. This is by Cauchy Shwarz less than or equal norm x plus 2 norm x norm y plus norm y squared. This is by Cauchy Shwarz. We prove it. This is Cauchy Shwarz norm xy dot y absolute value x dot y less than or equal norm x norm y here. So we use it here. Cauchy here, Cauchy Shwarz here, we use it here, and this we come back, this is equal to norm x plus norm y all square over brackets. And of course if we take the root of this, we get root x plus y less than or equal norm x plus norm of y. So we get the triangle inequality for norm. We get the triangle inequality for norm. This is finished proof of this proposition. I think this is enough for today. Thank you very much. Goodbye.